Okay, yes, Shakal. So as I was saying, right, we're talking about literal equations. You remember I said that we look at, we understand how all of this fits in the grand scheme of things. We're talking about equations. We're trying to solve for something, right? With literal equations, obviously now there's many unknowns. We just have to make X the subject of the formula, or R the subject of the formula, or S the subject of the formula. That's what literal equations basically is, right? But like in the video, you would see here that I talk about just like four different questions that you could possibly get and how to apply yourself in those scenarios, right? But like see, like in this question here, there's it here. You can factorize to isolate a variable. So if I told you to solve for x here, the only way I could do it, because these are unlike terms, right? I could only do it by taking out x as a common factor. Can you see that? And if I solve for x now, I need to remove whatever's not x. Remember using the BODMAS in reverse. Since this is multiplication, I have to make use of the multiplicative inverse. So I'll divide both sides by y plus 2. Y plus 2. That and that'll cancel, so we're left with 10 over y plus 2. And that's how you solve. Right, so there's an instance where you have to find, like here you can see, if you have fractions, multiply by the LCD and so on. It's all there, right? But you'll know how to apply yourself in these different scenarios. Um, yeah. Okay, so that's that for literal equations. Okay, let's move on to the next topic, which is exponential equations. So now the exponent is the variable, or x is the exponent. And so the way we would do that now is we have here 1 over 3 to the power x minus 1 is equal to 27. So if I look at this here, the first thing I have to do, right, when you look at exponential equations, there's it here. Exponential equations, I can only do one of two things, the rule of factorization. But I did mention something about factorization when I discussed exponential expressions. I said that you'll only use factorization if you could see a plus or minus sign. If you can't see it, then there's no point using it. And I've already explained why that is the case, right? And so if we go back to this here, right? We have to use the rule. What's the rule? The rule is that whenever you have two exponential expressions equal to each other, if the bases are the same, you can drop the bases and equate the indices. And so here, if I want to make the bases the same, what do I need to do again? Prime bases. Can you see? That will not tell you this is the first rule for any exponent question that you're given. And so if I do that, this will be 1 over 3. In fact, this 1 over 3 is not even a prime number. So how can I make 1 over 3 at the prime number? Is using negative exponents. So this will be 3 to the power minus x minus 1. Can you see that? So just by swapping the numerator and the denominator, I have to take out a minus sign. We did not change the question, we re-expressed it. And this 27 will be 3 cubed. And now since the bases are the same, I can drop the bases and equate the indices. And then we can solve. Minus x plus 1 is equal to 3. Minus x is equal to 2. X is equal to 2. X is equal to 2. And done. As simple as that. Right? So again, see, prime bases, 1 over 3 is not a prime number. Right? How can I make 1 over 3 a prime number? If you put it in the calculator, you won't be able to do it. Right? So there's something else that we have to use. Can't do it. Right? So there's something else that we have to use, and that's in fact the negative exponent. Once you do that, then you have to convert this here. See, prime bases are very important for exponents. Okay, and then the last one here is an inequality. So if you have 3 into, so it'll be 3 into 2 minus 3x greater than or equal to 15. Right? We're dealing with an inequality. The only thing that you need to remember for an inequality is whenever you multiply or divide by a negative, right? Change the direction of the inequality sign. Change direction of inequality sign. I'd write that down. Inequality sign. And so if we do that, Right, remember again, we're trying to solve for x, make x the subject of the formula. So what we'll do here is this will be 6 minus 6x greater than or equal to 15 minus 6x is greater than or equal to. See, I'm going to subtract by 6 on both sides. So therefore, I don't have to change the direction of the inequality sign. But as soon as I am dividing by a negative, then the direction of the inequality must change. So this will be x less than or equal to 9 over minus 6 is 3 over 2, minus 3 over 2, minus 3 over 2. Right, so that's minus 1.5. Okay. So yeah, and so if you look at this from a mathematical standpoint, if I look at this here, this is it's a linear function that has a negative gradient. So I think it should look something like this here. There's it here. And so this here is minus 3 over 2. Okay? And so we want to know for what values of x, well, in fact, it won't. Okay, so we want to know for what values of x will this linear function be greater than or equal to 15, right? So what values of x will this linear function here be greater than or equal to 15? And so what we're technically doing is we're saying, okay, I want to find out where is it equal to 15. Wherever it's equal to 15, then we're going to find out where it'll be greater than or less than. So I have to sketch it out here. This will be 2 into, or is it 3? 3 into 2 minus x. It'll be 3 into 2 minus 3. Yeah, it's something similar to what I had, right? Minus 1.5. When x is minus 1.5. See, there's it here. There's something wrong with this question. Okay, but yeah, you can see x values, the x values, every time it's less than minus 1.5, it outputs. See the y values, what is it outputting? Values that are greater than 15. Right, so that's what we need to remember. Okay, so yeah. So that's that there, right? Oh wait, this is what we did wrong here. See. That's why it's not making sense. I'm adding instead of multiplying. Okay, so this will be 3 times 2 is 6 minus 9x is greater than or equal to 15. And so minus 9x is greater than or equal to 15 minus 6, which is 9. Therefore, x must be less than. See, now we're dividing by a negative. So we change the direction of the inequality sign, and 9 over minus 9 is minus 1. And so watch, look how brilliant this is. You see, if I come back to this function, see at minus 1, the function is equal to 15. So at minus 1, the function outputs values that are equal to 15. If I go anything less than that, it outputs values that are greater than 15, which is precisely what we wanted. I want to find out for what x values must I input into this function such that it outputs y values that are greater than 15. Because see, 6 minus 9x is the same as y. And you see, that's how we look at this is a function. That's the y values. So where is y greater than or equal to 15? It's when I input x values that are less than minus 1. And I hope you understand that, right? I hope I made that correction and I clarified that. Okay, and then we talk about simultaneous equations. A plus b over 12. So a plus b is equal to 12. And 4a plus 2b is equal to 44. 4a plus 2b is equal to 44. Right? If I look at this here now, I can see that we are dealing with two equations, equation 1 and equation 2. Right? When we talk about simultaneous equations, we use simultaneous equations when we have two unknowns. So there's an unknown here, A and B, is an unknown here, A and B. And so the general rule is that we require the same number of equations, as they are unknowns. So we require the same number of equations as they are unknowns. And so I have two unknowns, so therefore I require two equations. If I had three unknowns like x, y, and z, then I'll need another third equation. Very powerful conclusion, because when you get to word problems, this is why we use simultaneous equations. Okay, and so yeah, if we solve for this, we can use substitution or, sorry, 1 minute. Yes, and so if we use substitution here, we can make one of these two variables the subject of the formula. So I'll say B is equal to 12 minus A. I'll call this here equation 3. Then I'll say substitute equation 3 into equation 2. So substitute equation 3 into equation 2. Second thing you need to remember, you require the same number of equations as the unknowns. The second thing that you need to remember is that whenever you substitute, you get rid of one variable. Rid of one variable. Right. So when I'm doing the substitution here now, I'm getting rid of what? The B. And so it'll be 4A plus 2 whenever you substitute parenthesize is equal to 44. Okay. And so why was this so important? The substitution step, this is why this is a technique, is because now I have an equation in terms of one variable. So I went from something that I don't know how to solve with two unknowns to something that I do know how to solve. This is why this technique exists. And so now we can just use normal maths. Plus 24 minus 2a is equal to 44. Right, that'll be 2a is equal to 44 minus 24 is 20. Therefore, a is equal to 10. But remember, what is the primary purpose of simultaneous equations? Is to solve for two unknowns. I have one unknown, let's solve for the other. Take this and put it back into equation 3, because I can take this and put it back into equation 3, 2, or 1. But if you need to make a smart decision. This is already in the form b is equal to something. If I'm going to use this, then I have to make b the subject of the formula. If I'm going to use this, then I have to make b the subject of the formula. This here, the b is already the subject of the formula, right? So that's why I can use this one. And so I'll say substitute a equal to 10 into equation 3. Substitute a equal to 10 into equation 3. And then we'll have b is equal to 12 minus 3 whenever you substitute parenthesize. And 12 minus 3 is what? What is 12 minus 3? 9. Right. Now, yet again, we are working with what? We're working with what? We're working with simultaneous equations. So what we have here now? We have 10 and 9. You know what this is. And you know what this is. These are two functions. Because if I re-express this as x plus y is equal to 12 and 4x plus 2y is equal to 44. And if I sketch these two functions, the points of intersection between these two functions, I'm just going to sketch it randomly here, something like that and something like this. Where these two functions meet, that's where you get a coordinate, a and b. This is why you get a coordinate, a and b. So that coordinate there will be 10 and 9, right? Obviously, it's not drawn accurately, but these are two functions. So they can call it whatever variables. If you sketch these two functions, you would find that the point of intersection between those two functions is in fact 10 and 9. And so what we're saying is, if I look at this here as function 1 and function 2, right? Where or what a value must I input year and year and year such that we output such that we output the same y value where they coincide, which is exactly at the point of intersection. So this is why we can do, like if we had the function like this here, y is equal to 2x plus 1 and y is equal to 3x plus 4. And I tell you, find the point of intersection between these two functions, you'll equate them. I have two unknowns, x and y, or y and x, right? I need the same number of equations as the unknowns. I do have that. And so now I can solve simultaneously. But now, I can just, do an immediate substitution here. I can just say, okay, substitute y equals to that into equation 1 and I can solve. But this is more on the graph and interpretation type question, which we do later on, but you should have done this. But yeah, so it's a point of intersection. Can you see how we're using it in maths? Right, and then we have word problems. We have word problems. Right, so let's do this. Bring it here, right? Okay, let's do this. All right, George is 7 times as old as his son, and in 25 years' time, he will be twice as old as his son. Calculate his son's present age. Now, you see, right, listen to this, whenever you're dealing with the variable of time, always make use of a timeline, right? Because that's what, when you do accounting, right, if you do accounting, in accounting, we make use of the financial year, we make use of a timeline. It's the exact same thing. You're trying to visualize time, use timelines. You're trying to visualize equation and expressions, use functions. These are visuals that enable us to see things. And so when you do this, you'll always be working with either current and future or current and past or future and past, whatever it is. But it's always past, present, and future. And so if you look at this here now, we're dealing with current and in 25 years time, future. So we got current and we have future. Okay, currently, George is 7 times as old as his son. Now, this is what's very important. If I put George here and I put the son here, I can express this in 2 ways. If George is 7 times as old as his son, right? If I call his son's age x, then George will be 7 times x. Alternatively, which is something that you should not do, if I call George x, then his son will be a 7th. You divide by 7. It'll be a 7th of George's age. We don't like to work with fractions, so we take that out. And let me say that again. His son is x, then George will be 7x. If George is x, then his son will be 7 divided by x. It'll be a 7th of his age. I think about it, if George was 2 times as old as his son, then his son will be half George's age. Same thing we're doing here. Right? But now we're not going to work with fractions, so that's why we keep it like this. Now listen to this. What is x? This is why, why people can't solve or they struggle with word problems, because they don't understand the variable. X is his son's current age. So this will be years old. George, 7x is George's current age. So this will be 7x years old. This is a number. It's not a variable. As far as I'm concerned, when I look at this, this is a number to me. This is a number. Right? I don't look at it in any other way. Okay, in 25 years' time, if I take this here, in 25 years' time, I am going into the future, adding 25. And what's going to happen in the future is George's current age is going to increase by 25, and his son's age is also going to increase by 25. See, we're not learning, we're not trying to study questions here. We're looking at it from a realistic standpoint. Every word means something. In 25 years, that will be it'll be plus 25, and then both their current ages will increase by 25. He will be twice as old as his son. In 25 years, he will be twice as old as his son. In 25 years, he will be twice as old as his son. You know what that means? It means in the future, at this point, in the future, at this point, he will be twice. So it'll be George's future age. This is a number, not a variable. Will be the same as his 2 times his son 2 times his son's future age, which will be 2 times this number. This is something years old. That's something years old, right? And you know why this is so powerful? When you're working with word problems, there has to be a link in the question. So from year to year, there was no link. There was no link. What links these two year is the fact that in the future, their ages or this person's age will be double. George's age will be double his son's future age. Right, I hope you'll understand. So in the future, George's future age will be two times his son's future age. That's why we put it there like that. Right? Okay. And so if we do this now, we can just solve this like a normal equation, which is equal to 2x plus 25. Sorry, plus 50. Yes. Bring this across, it'll be 5x. 50 minus 25 is 25. X is 5. What is X? Go back and define your variables. X is his son's current age. And so, in fact, we did solve for his current age. And what's powerful about word problems is that once you define your variables correctly, it's so simple. And once you define your variables correctly, then you just express everything in terms of that variable, right? Because yeah, you express everything in terms of the variable. Now, see, I could have done the exact same thing. I could have said like this here. I could have said George is X, his son is X over 7. And so when I came down and I solved for X, X would have been George's current age. So to get his son's present age, I have to say it's George's current age divided by 7. Can you see what I'm saying? Whatever I define to be my variable, I have to shift everything and express it in terms of that variable. So now this here will become x plus 25, and this here will be x over 7 plus 25. These are numbers and not variables. So it'll be his current age plus 25. It'll be the son's current age. This is a number and not a variable, plus 25. And then I'll say, okay, in the future, this age here, George's future age will be 2 times his son's future age. And so now it'll be x plus 25 is equal to 2 times x over 7 plus 25. Right, can you see that? Plus 25. And then when you solve for this, you get x is equal to 35. I'm certain. Solve it and you'll see. X is equal to 35. So to get his son's age, it'll be 35 divided by 7, which is 5. So here you'll get 5. Here you get 35. See, now here we got 5. Here you'll get 35. Both ways get you to the same thing. As long as you're defining everything in terms of ITO, in terms of everything needs to be defined in terms of X, in terms of very important word. Everything needs to be. So when you're changing the definitions of these variables, you need to be very mindful of how you're working with them. Okay. So yeah, so that's word problems. Yeah. Yeah. See, now we're just gonna basically do so like repetition now, right? Can you see here? Here I have an exponential expression. Exponential expression involving what? Multiplication and division signs. If it does that, then what we use? See, theory remains the same. That's why I don't do so much questions, because we're just gonna basically do the same thing over and over. There's it here. Convert, distribute, separate, simplify. Same idea. I do that for this question, you get the same answer. Yeah, I'm required to factorize. If I have to factorize this question, the first thing that I have to do is pull out an HCF. After I pull out an HCF, then look, so if I pull out the HCF, 3 into x squared minus 1, it can't just stop there, isn't it? So then if I do this now, then I come all the way back down to that mind map. It'll say distribute and check. If I distribute, yes, I do in fact get that answer. But when I check, I realize that I can go a further step for this one, right? Because if I go back to the top, I can't take another HCF, but I can do dots for this. And so this will be 3 into x plus 1, x minus 1. That's what it means by, or that's what it means to have an expression factorized fully. Same here too. If I do this, I have to take it in HCF. So this will be 10 into 2x squared plus 3x minus 2. Right here, you can choose to use a calculator or solve it. Right here, if I look at this here, I haven't ever seen a question like this, isn't it? I never saw something like this here. So how am I going to do this? Take out the brackets for a moment, right? Watch here. I know how to work with something like this. Why? I can't take it in HCF, but I can see 4 terms. If I see 4 terms, then I'm going to use factor by grouping, right? And if you do that, they just basically gave you help here. They put that in one bracket. You can't factorize the HCF here. So let's work with this here. So be minus a into x minus 2y. And then we have a common binomial factor, so we can simplify. So it'll be x minus 2y. There's an invisible 1 here. So it'll be 1 minus a. Can you see that? And that's how we solve. So it's the exact same ideas. Same ideas. Rinse and repeat. Yeah. See for this here as well. We try to get rid of fractions, right? We try to get rid of fractions. We don't want to work with fractions. And so when you have a fraction, if I multiply both sides by 5, guess what? I'll get rid of this fraction because 5 times whatever, I'll get rid of that fraction. But then I'll still have this 3 here. So what I need to do is I need to go then multiply both sides by 3, right? Effectively, what I did was I multiplied both sides by 15. And so the general rule is when you have many fractions, multiply both sides by the LCD. Multiply both sides by the LCD. Right. And when you do that, if you multiply both sides by 15, then you'll have like a normal, like I like to think of it like a equation on a single line. Yeah, you can see this is an equation on a double line because you have a fraction. You'll have everything on a single line, a single straight line, and then you can simplify and solve. Here you're trying to, what do you call this? You're trying to solve a quadratic equation. To solve for the quadratic equation, you need to make sure the right hand side is 0, and then you factorize. Factorize, go back to the first step. Pull out an HCF, check the number of terms, then factorize. You can put it in your calculator or factorize normally. All right, so that's very straightforward there. Yeah, then if you look at this one here, Timothy, a grade 10 learner, was challenged by his friend that very few learners could get this math riddle solved. Help Timothy solve the problem. Divide 57 in 2 parts so that 1/2 of the greater part is 11 more than 1/5 of the smaller part. Suppose the greater part is x. Yes. Right, so let's look at this now, right? Divide 57 into 2 parts so that 1/2 of the greater part is 11 more than 1/5 of the smaller part. Bit of a confusing one. All right, but let's do it. You got 57 here. They want to take 57 and divide it into 2 parts. Right? There's one part here. There's another part here. We don't know what those parts are. Right? So that 1/2 of the greater part is 11 more than 1/5 of the smaller part. Now you see when you look at this here, why word problems, another reason why word problems are so hard is because you need to read ahead. They say suppose the greater part is x. So if I call this here the smaller part and the greater part will be x. So you have a smaller part, you have a greater part from this 57, right? What did I just speak about when we did the word problems? I said that there has to be a link. If there's no link between these things, then there's no point. Even in maths, everything has to link. If there's no link, then there's no point in even doing maths. This is why I create mind maps. This is how I linked term 1 work with term 2. There has to be a link. And unless, a section stands on its own, but that's not even the case with maths. So we're saying that 57, I got it into 2 parts, a smaller part and a bigger part. The greater part is what we're calling x. So what links this two is the question. I must divide it so that 1/2 of the greater part, so 1/2, 1/2, 1/2 of means multiplication, the greater part, x, is meaning is equal to, is the same as 11 more than, so it's 11 plus 1/5 of the smaller part. 1/5 of the smaller part, SP. But what is the smaller part? If this is 57 and the greater part is x, then this has to be 57 minus x. Because the smaller part plus the greater part must give you 57. SP plus GP must equal to 57. So if the GP is equal to X and the entire thing is 57, then SP, just using normal algebra, is 57 minus X. Yes? And so now we have 1 over 2X is equal to, can you see what links this to? What links this to? It's that half of this amount, this is a number and not a variable, half of this amount is equal to 1/5 of this amount plus 11. It's equal to. And so this will be 11 plus 1/5 into 57 minus X. And straightforward, simplify, and you'll solve it. Right, so if I did it much more neater here, it is best we make use of a diagram so that we have a better idea of the problem. Since we know that 57 is divided into two parts, now listen to this. Yo, I didn't even, yeah, this is such a powerful conclusion. Not equal parts. That's very powerful. It's just divided into two parts. If it was divided into equal parts, then I would have said 57 divided by 2. Very powerful. Very, very powerful conclusion. Right? Yeah. So it's divided into two parts and not equal parts. Okay? And that one of the parts is called X, then the remainder has to be 57 minus X. Visually, this is 57, then 57 minus X, and that'll be X. Right? Yes. We are also given that half of the greater part, so half of the X, and see the word is implying equal to. Right? The word is implying means indirectly means equal to. Is 11 plus 1/5 of the smaller part, which we found to be 57 minus X. Mathematically, we write half over X is equal to 11 plus 1 over 5 into 57 minus X. Now we can solve for X and find the greater part and the smaller part. Right? If I solve for X, what is X? X is the greater part. Remember, we see these as numbers and not variables. Because if we see them as variables, then it gets confusing. And if you solve, you get X to be 32. And so we say that the greater part is 32, but the smaller part is 25. Okay, guys. Yes. Yeah, can you see this? Exponential expression. Exponential expression, what? Involving plus and minus signs. You're going to say, do the same thing. Convert, distribute, separate, simplify. But when you come to the simplify step, you're going to use factorization because we can see the plus and the minus sign. Okay. When you multiply and divide fractions, it's up and times, isn't it? So it'll be A over B divided by C over D is the same as A over B multiplied by D over C. When you multiply fractions, you multiply numerator to numerator and denominator to denominator. And we solve. Simple stuff, right, guys? But here now you can see at the end, your last answer, you're going to say X cannot equal to minus 5. There's a restriction. I see fractions, I know that there's a restriction. I factorize. If I look at this question, I can't take out an HCF. I can see two terms. I'm going to make use of one of the techniques for special binomials. Which of the two I'm going to use? Is it dots or sum and difference of cubes? It'll be sum and difference of cubes. So it'll be the difference of cubes. And so if I have x cubed minus y cubed, then it'll be cube root the first term, copy the sign, cube root the second term. Then square the first term, multiply both those terms together, and change the sign of the first bracket plus y squared. Done. Simple stuff, right? And so now you're going to take the same identity and apply it here. So if I cube root the first term, it'll give me 5. Cube root the second term, I'll get minus 3m. Yes. Square the first term, 25. Change the sign, multiply both those terms together, 15m, and square the last term, which will give me plus 9m squared. Right? And so that's everything there now. Again, we've solved the first part. Now we have to go back and distribute. If I distribute, I'll get that there, in fact, right? But if I do the checking step, I'll realize that I can't simplify that further. Remember, I said that that's an infactorable. It's infactorable. I'd put it in your calculator, you'll see, and that will always be the case. This here will always be infactorable. So don't even go waste your time looking. I'm telling you now, it won't. All right. And if you want to know why, if you sketch this as a function, it'll lie on top here. Right? It won't touch the x-axis. So that's why we can't factorize. Okay. So yeah. Yeah, okay. See here too as well. If you look at this here, we have to solve this inequality. Remember, I said the inequality. It's only when you multiply or divide by x that you do change the sign of the or the direction of the inequality sign. And so we have to simplify this now. I'll get 6x plus 12 minus 3x plus 9 less than 0. I can simplify like terms here. So it'll be 6x minus 3x is 3x plus 12 plus 9 is plus 21 less than 0. Then 3x is less than minus 21. I took that across. Remember, I only subtracted by 21 on both sides. I did not divide. And then if I divide both sides by 3, then I'm left with x less than minus 7. Now, I think they asked us to use interval notation. When you're working with interval notation, right, there's this interval notation and there's set builder. When you're working with interval notation, you're using brackets. When you're working with set builder notation, we're using inequality signs. Right. And in both instances, we just basically, the core of stating these sets is you want to state the max, the minimum, and any restrictions. That's it. That is all you got to remember. Max, minimum, any restrictions. And so if I do that, if x has to be less than minus 7, the minimum value is what? Minus infinity. The maximum value is what? Minus 7. Then you have to ask yourself, am I including these extremes? Do I include minus infinity? You can never include minus infinity because infinity is intangible. It's on the extreme left. We don't know what the number is, so we can never include it. And minus 7, because we don't have an equal to sign here, we can't include it. And so what we're saying is, I can input, you see what this here? This is a set. So if you think of this here as a circle, and you think of every element in between this here exists in the circle. If I just randomly pick one from it and I input it into this equation, into this expression, I'm certain that I'll output a y value, or I'm certain that I'll output a value that'll be negative. So into this expression, if I have to input any x value that is less than minus 7, not equal to, but less than minus 7, I am certain that this here will come to some negative value. Let me prove it to you. And so if I do this, see wherever I'm putting x down, I'm going to put a bracket. Right? Minus 3. Right, check here. Any value less than minus 7, right? Watch here. I'm going to put in, as long as it's less than, right? I'm going to put in minus 7.1. Right? Minus 7.1. Right? Minus 7.1 is just a fraction to the left. Look at this here. I'll put this on a timeline. If I put this on a number line, see, you use numbers to represent number lines. You use timelines to represent time. We use functions to represent equations, visuals. We need to see these visuals. And so if this here is minus 7 and this here is minus 8. See, minus 7.1 is slightly here, just to the left. And that's what this mathematical statement is saying. It just has to be slightly less than 7, minus 7, and it will output a negative value. And when I press equal to, can you see? Negative. But if I output a value that's just a